Visions, but only illusions. Looks like we've finally gone live. Okay, solution stoic. So we do chemistry with solutions. Means we do stoichiometry with solutions. So remember, all roads lead to mole. So in this case, rather than working with a dry substance and converting to moles, we're going to be working with solutions and converting to moles. No real big deal. So reactions in solution are just like any other, except they're damp. So if you drop a pellet of zinc into hydrochloric acid, you will produce zinc chloride and hydrogen gas. Now notice that I finally started putting the subscripts on there indicating the state of matter. So we drop solid zinc into aqueous HCl. Aqueous means it's a solution rather than, and not a liquid. Liquid HCl would be just pure hydrogen chloride in liquid form. Wow, that would be incredibly dangerous. And zinc chloride, AQ, also dissolved in water. So these are going to be solutions. And then hydrogen gas. Okay. So if you drop 1.278 grams of zinc into 125 mils of 0.8755 molar hydrochloric acid, hydrogen chloride refers to the solid. What mass of hydrogen will evolve? Okay, so we're dropping a solid into a solution. So we got two different ways we need to calculate moles. We're also going to need to balance this reaction. Fortunately, that is super duper easy. So first up, let's go ahead and balance that reaction. Zinc plus 2HCl yields zinc chloride plus H2. Like I said, super easy. Okay, so we have a solid being dropped into a solution. I'm giving you the starting quantities of two different reactants. That means this is a limiting reactant problem. So you're going to have to convert both of them to moles and then compare those in the context of the reaction. So 1.278 grams of zinc and 125.00 mils of 0.8755 molar HCl. So for our zinc, I'm going to do brown because it's a solid, earthy. So 1.278 grams of zinc times, bring out the periodic table, 65.38 grams per mole. We're actually dividing. So calculator, you gotta keep them calculated. 1.278 divided by 65.38 is 0.01955 moles of zinc. And because it's a liquid, I'm going to go ahead and do the HCl in blue. So we have a volume and we have a molarity, so we don't need the periodic table for this one. 0.8755 moles of HCl per liter times 0.12500 liters. Don't forget to convert. I gave it to you in mils, but molarity means liters. So be careful about your units. Definitely always pay attention to your units. Otherwise, you could get in a horrible car accident. Okay, so 0.8755 times 0.125. 0.1094 moles of HCl. All right, so even though the HCl gets used up twice as fast, okay, there's way more HCl. Okay, there's 5 times as much HCl as there is zinc. Okay, we only needed twice as much. So the zinc is going to be our limiting reagent. All right. Yeah, I mean, if we multiply this by 2, to convert to moles of HCl, we'll use 2 moles of HCl for every 1 mole of zinc. That would get us 0.03910 moles of HCl. So we need the 0.03910 moles. We have 0.1094. We have way more HCl than we need. The zinc is our limiting reagent. So now let's go ahead and calculate how much hydrogen we can produce based on our limiting reagent. So we've already done step 1 of the stoich here. So it's 0.01955 moles of zinc times 1 mole HCl per 1 mole of zinc, and I'm doing it in red because hydrogen's a gas. And I asked for mass, so 2.0158 grams per mole for H2. Oops, not HCl, H2. This means we're going to, well, theoretically, what is the theoretical yield? So 0.01955 times 1 over 1 times 2.0158, 0.03941 grams of hydrogen. And that is our theoretical yield. So solution stoich is pretty much exactly the same as regular stoich. It's just you have another way to calculate moles. That's all. Okay. Otherwise, you just do regular stoichiometry. Once you've gotten to moles, regular stoich from there on out. You compare your two things in the context of your balanced reaction to find out which one is going to run out first. This could be a percent yield problem. It could be a limiting reactant problem. It could be just straightforward stoich. Doesn't matter. It's all just the same stuff with another way of calculating moles. That's it. Okay. So now let's look at aqua regia, the royal water, because concentrated nitric acid was capable of dissolving gold. Possibly. It might have been a mixture of nitric and phosphoric. Anyway, so gold plus nitric acid makes gold 3 nitrate and hydrogen. What volume of nitric acid is necessary to dissolve 565.5 grams of gold? Okay. So this is, like I said, a straightforward stoich problem, not even a limiting reactant problem. Although, once again, we need to balance the reaction. AU plus HNO3 yields AuNO3 3 plus H2. For those of you who are still having trouble with these, I recommend you pause, try to balance it, and then come back. Okay, if you couldn't solve it, I see a 2 here, I see a 3 there, and I see that they're both together. I know that I'm going to need to double this. So if you're having trouble with that, now know that you need to start by doubling this and then come back. Okay, hopefully you solved it. You need 6 of these, 3 of these, and 2 of these. All right, so there we have our balanced reaction. So how much of our nitric acid do we need to dissolve that much gold? That is to say, how much do we need to fully react with that much gold? I'm going to do orange because we're talking about gold. Gold isn't really orange, but close enough. I could do yellow, but you wouldn't be able to read it. All right, so 565.5 grams of gold times, I definitely don't know the molar mass of gold. We never work with gold in chemistry because this is expensive. 196.97, so 196.97 grams of gold for every mole of gold. Then we need 6 moles of nitric acid for every 2 moles of gold. Now, we have moles of nitric acid, but we're not working with solid hydrogen nitrate. We're working with a dissolved form of nitric acid. Specifically, we're working with 1.250 molar nitric acid. And remember, that means 1.250 moles per liter. So let's go ahead and just 1.250 moles of HNO3 for every liter of HNO3. Okay, that's kind of hard to see, but that's an L. All right, so now this will get the volume of nitric acid that we need to dissolve this 565.5 grams of gold. divided by 196.97 times 3 divided by 1.25. We're going to need quite a lot. That is a hefty amount of gold. It's, in fact, more than 2 moles of gold. So we're going to need 6.890 liters of 1.250 molar nitric acid. That's kind of a lot. Why would you want to dissolve that much gold? Maybe you're trying to plate something with gold. Electroplating. Electroplating, I believe, one of the Central American native kingdoms developed a method for electroplating things with gold, which is pretty neat. I think they also invented it in the Middle East. They invented crude batteries, probably for much the same reason. All right, here's another one. Sodium plus water makes sodium hydroxide and hydrogen gas. Then you can mix sodium hydroxide and sulfuric acid to neutralize the... Oops, I have the thing up. So, mixing sodium metal with water produces sodium hydroxide and hydrogen gas. Then you can use sodium hydroxide to neutralize sulfuric acid. You'll make sodium sulfate and water. So, if you had a giant pond full of concentrated sulfuric acid, how much sodium metal would you need to throw in there to completely neutralize that sulfuric acid? This is not a completely ridiculous question. Mine tailings, just the waste stuff left over from mines, tends to produce very acidic runoff because it has lots of these sulfates in it, magnesium sulfate, calcium sulfate, things like that. So when water runs in there, especially if it just steeps in the water for a really long time, it can produce sulfuric acid. So mining waste can produce just these incredibly toxic environments. All right, so we have two chemical equations, and we're going to need to balance them both in order to find out how to completely neutralize, completely react 25,670 liters of 0.01278 molar sulfuric acid. All right, let's get cracking. Sodium plus water. I'm going to do this one in green because it's a base we're talking about. Sodium plus water makes sodium hydroxide and hydrogen gas. And then we have sodium hydroxide plus H2SO4 yields sodium sulfate and water. All right, two of these and two of these. All right. Oh, you couldn't see me doing any of that. I'm such a doof. Okay, so I balanced the chemical reactions while you weren't looking. So 2 sodium plus 2 water makes 2 sodium hydroxide and 1 H2. 2 NaOH plus H2SO4 yields sodium sulfate and 2 water. Now I'm going to let you in on a little secret. You can add chemical reactions together. It's not a secret at all. But you just have all your reactants end up down here, all your products end up down here. But anything that appears on both sides of the equation cancels out. Okay. So for example, we have 2 water up here. We have 2 water down here. So our waters, boop, cancel out. Likewise, we have our 2 sodium hydroxide on either side, so they cancel out. So when we add these 2 reactions together, what we end up with is just 2 sodium plus H2SO4 yields Na2SO4 plus hydrogen gas. Would sodium metal react with sulfuric acid in quite this way? Probably. It's just that if you tried to do that, you'd be adding a solid to a solid. If you were to throw sodium metal into water, you would get this reaction up top along with this second reaction down on the bottom, as well as this reaction as we've written it right here. Yes, I can see this happening. It would just be kind of weird. Basically, if you were to have solid this hydrogen sulfate and solid sodium metal, and you mix them together, this would probably melt and then you'd get a massive explosion from the hydrogen gas. I really wouldn't recommend trying it. But doing it this way, even if this is how we'd actually do it by throwing it into liquid, we can pretend. Okay. So now, having balanced our two equations and rambled for a bit, this is just another straightforward Stoic problem. We know how much sulfuric acid we have because we know the volume and we know the concentration. So that means we know the moles of our sulfuric acid. And knowing the moles of our sulfuric acid, we can do Stoic to find out how much sodium we will need. So let's go ahead and do that. I'll do the acid in red. We have 25,670 liters of our sulfuric acid. And we have a 0.01278 moles of our sulfuric acid per every liter of that solution. So the liters will cancel, leaving us with moles. And then we can go ahead and do our Stoic. How much of our sodium metal do we need? Well, it's 2 moles per 1. So times 2 moles of sodium for every 1 mole of H2SO4. But then, of course, I was pointed about it, we need mass of sodium. So 22.990 grams of sodium for every mole of sodium. And that will get us our answer. 25,670 times 0.01278 times 2 times 22.99 is, oh wow, 15,000, we have 4 sig figs, so it's, 4 sig figs, 15,080 grams of sodium, or a 15.08 kilogram block of sodium. That is, that's a lot, that's a lot of sodium. Let's see, I would guess that would just be a big chunk of sodium. That's ridiculous. All right. But that is how we do solution stoichiometry. It's literally just the exact same stuff as any other kind of stoic. With just, like I said, all we've done this entire time is just add another step, another thing to do. And so limiting reactant, percent yield, and now we just have another way to get to moles. That's all we've done. Okay, so that is it for talking about solution stoic. I will see you in the next video for the end of Chapter 6, when we talk about titrations. See you then.